Okay. So I'm Connor. I'm from Carnegie Mellon University. I'm a PhD student in Sarah Magetich's group. Today, I'm going to be discussing monopole-like excitation lifetime and their experimental observations via spin canting and magnetic tunnel junction artificial spin ice using tunnel magnetoresistance. So first, our basic bit is a super paramagnetic tunnel junction. So for those of you that aren't familiar with what a magnetic tunnel junction is, it is two ferromagnetic layers separated by a tunnel barrier. In our case, we're using in-plane MTJs. The fixed layer, when you're parallel to it, it's a low tunnel magnetoresistance. Anti-parallel leads to a high tunnel magnetoresistance recording. The separation of the parallel and anti-parallel state is going to be dependent on the thickness of the tunnel barrier, which will be that interlayer exchange coupling. And then the energy barrier for super paramagnetic tunnel junction will be around 8 to 12 kT. But we know that the energy barrier is a function of field. So we know that the dwell time distribution, which is a Nail-Arrhenius equation, should be a function of field. We also know that it's characteristic for the tunnel magnetoresistance to have a function of angle. So as the magnetization cants, the tunnel magnetoresistance should also show that as a function of a cosine function. So we arrange these magnetic tunnel junctions into artificial spin ice. Many of you may or may not know what artificial spin ice is. I find it's either you do or don't. Basically, in this case, we take basically ferromagnets and we arrange them magnetostatically so that they're magnetostatically coupled. In traditional cases, these are dominated by large shape anisotropies, so the energy barrier is very large. So the explicit configuration of each of these spins can be characterized with something like magnetic force microscopy. But all of these cases can be simply characterized as having these. There's two end states, but they can be characterized by they can be characterized by having type 1, type 2, or type 3, which is dependent on the amount of magnetostatic energy that exists. In our cases, we're going to be dominated, type 1 dominated. Each one of these dipoles can be given this fictitious magnetic charge. It's absolutely fake, but the idea is that one can take one of these nodes that's identified here as pink, green, or blue, and it can have a charge of 0 or non-zero. And when you have a charge of 0, you follow the spin ice rule: 2 spins out or 2 spins in. When not, then you have what they call an emergent magnetic monopole. In any case, it's just an excitation or a magnetic defect or a magnetic excitation. For us, we want to use super paramagnetic tunnel junctions, so we know that we want to reduce their shape anisotropy. In fact, we reduce it to near zero, as close as we can get with EBM. System without a coupling field would have a continuous degree of freedom, so it would follow the dwell time distribution would follow some simple beta of a stretch exponential. But if we build this on an MTJ stack, our synthetic antiferromagnetic layer develops a coupling field for a preference, and we can end up having a preference. We can break the symmetry of dipolar XY ASI. And just as a simple demo, you can actually have different regions of domination if you consider the uniaxial anisotropy domination in plane. Without considering that coupling field, you can have domination for a significant amount of times in the magnetostatic contributions. So what we're really looking for is maintaining that complex interaction landscape, but increasing the reaction time, so the frequency in which the individual magnetization relaxation processes occur inside that single nanomagnet. And then we'll have that SAF, which breaks the coupling field, the symmetry. So to do this, we use conductive atomic force microscopy. We use tunnel magnetoresistance. With CAFM is very simple. It's taking an AFM tip that's conductive and making direct electrical contact to one of these devices. In it, we can measure as a function of, we sweep the field in the X direction, and we also can measure time dependence, continuous time dependence of one of these MTJs. What we find with field is that there are two main behaviors. One, it is either an X device that telegraphs between parallel and anti-parallel. The only difference in this case is that it telegraphs at nearly zero field, or it observes a rotation in which the magnetization no longer lies along that sweeping field. So we observe a more Y-like device. So we basically give those two devices X and Y. We also observe a small fringe field observation, but that is we observe a checkerboard-like pattern. So by taking that checkerboard-like pattern, we can then imagine what an X device would look like. It is surrounded by 4 Y devices. When we look at the time dependence of the tunnel magnetoresistance, we actually observe a two-state system, but we observe a system in which the characteristic average dwell time is actually changing as a function of time. And so if we take an autocorrelation of these different windows, we should observe a nearly stochastic autocorrelation that has different characteristic dwell times. And so what that really means is that we have a magnetostatic coupling between some Y device and the X devices, in which the organization of the Y, so the active corresponding magnetization of a Y device is dictating the dynamics of an X device. For a Y device, though, that is everything that I've talked about is no longer true, to a sense that things become very complicated. So I talked about tunnel magnetoresistance being a function of angle. It turns out for Y devices, when you're surrounded by 4 X devices, the individual magnetization dynamics of those devices lead to these long metastable Canting baseline states in which the magnetization can actually take these metastable states. And so this is what we call a metastable Canting's baseline state. If we continue to look at these states, or before I move on, you might notice that there are these spikes in these data sets. What it ends up being is simply, if we look at a low energy configuration, in this case, the type 1 configuration from earlier that I showed, and we discuss what direction a magnet might move, then it would seem that that magnet might move towards the coupling field. So if we imagine what happens when a nanomagnet switches, an X device switches towards that coupling field, we actually get a direct canting of that Y device. And what happens when you make a thermal excitation in an array of an already fairly stabilized metastable state, you get quick reversal of that state. So these spikes in the Y devices are responses to the X devices attempting to cause something to happen because they have two stable states, parallel or anti-parallel. If we continue to Y devices, we can actually pull out quite a number of data. We can pull out single long-ranging dwell time distributions. We can also pull out transitions between these metastable distributions in 200 millisecond window times. It's quite few we can actually do this with tunnel magnetoresistance, but it still doesn't allow us to look at what the actual spin configuration in the system actually is. So for that, we end up falling back to mu-3 to try to describe it. So instead of considering a basic node like they do in ASI, what we actually consider is the local magnetostatic field about a single device, so the nearest neighbors of that device. So if we consider a Y device and its local nearest neighbors being X, we already gave them two positions, either parallel or anti-parallel, or plus or minus X. And then if we actually calculate what the local magnetostatic field is, or the asymmetric local field from these devices, then we actually get a development of many different cases that we get. Basically we get either 90, plus or minus 90, 0, or some Canting state. And so Canting's origin is due to the asymmetric local field. And so if we end up taking these cases, which I just wanted to show you what case 1, 2, and 3 might look like, case 3 is really just a mixed state of these. And what ends up being the case is that if you take case 3, it's actually, if you take the node sum charge about any case 3, it's always non-zero. But experimentally, we have observed many different angles. So we have to extend this to the next magnetostatically dominant one. We chose the Y devices. We fixed them to plus or minus 90 degrees due to limitations in our calculations. And then we ended up choosing north and south because they have the highest contributions of magnetostatic field. By doing so, we were able to expand the number of Canting states, and we were able to observe quite a number of Canting states, even from such a simplistic model. We're also able to develop their energetic states. So we're actually able to observe what these spin configurations actually are. And when we do so, we can actually pick out which ones are or are not monopoles based on the simple definition that a sum of charge should be 0 about a node. And it turns out these double nodes actually always have some non-zero charge about them. The red here being cases in which they're considered perfect monopoles, and these purple ones being monopole-like, so they're EMM-like states. But it turns out that all of these Canting states are indeed emergent magnetic monopole-like. So when I show that we have these Canting states, we're actually looking at magnetic excitations in real time. So we can actually view these magnetic excitations, and we can compare the experimental and simulational results, and we can see that there are many different baselines of these states, and they can be identified relatively by this BCDE model. I want to just quickly say that the spikes tend to go down towards the parallel direction, but they also go up. I didn't want people to think that they don't. So the absolute opposite is same true, that you can also end up canting towards the anti-parallel direction and also observe a spike or a transition towards there. Now, the title of the talk was understanding the lifetime distributions of these systems. So the question is, how do we build a baseline, a dwell time distribution of a transitionally moving baseline? And so basically, we have to denoise a time signal without losing resolution of the tunnel magnetoresistance, and we can basically couple these to some threshold and some minimum dwell time distribution, or some minimum dwell time, and we can really build these clusters or these segments, and then we can actually cluster them by their means, and by clustering by their means we can actually fairly easily build up dwell time distributions for each of these metastable baselines. And by doing so, we actually observe that they do indeed deviate from log linear behavior, so that they have some previous state memory. It is also fairly easy to observe in this case that states that cant closer to the parallel direction, so the closer they are to 0 degrees, the more likely they are to observe these longer range dwell time distributions. It is also obvious that there are lower dwell time distributions at the low limit for all the Y device states. This would be because of the corresponding connections of the X device. We can do something different. We can do, instead of calculating the dwell time distribution, we can calculate a metastability distribution. So basically asking how long do we dwell in a particular metastable state. And the fact is that we can get, although we see lots of interactions at 50 millisecond time window, we saw lots of different clusters, we can actually observe these very long range metastable states in the Y devices. And this would basically allow us to make a conclusion that although we see lots of interactions in this ASI system, we need a collective multi-step reversal process to actually move between the baselines. So that would be a complicated interaction. And then there's a data repository for this data, and then the publication is pending. I want to thank our growers and the facilities at CMU and the NSF. All right, I'll take any questions now.
So, thank you very much, Connor. It was a really interesting talk. Unfortunately, I think we're out of time for questions, so I think we need to move on to the next talk. But I'd like to just mention that we can you can also ask questions to the speakers and discuss things in the chat or in Gather Town afterwards as well. So thank you very much, Connor, for a really interesting talk.
Thank you.